in this video, we're going to see the first example of some non-trivial sheaf on a particular variety X, which we take to be Pn. And these OX modules, they are called the twisting sheaves on projective space. So the input is that you fix n, the dimension of Pn, and then d, some integer. And for any non-empty open subset of Pn, you define the sections of this sheaf. So the sheaf will be denoted OPn of d. And on this set U, you define that the section should be symbols G over F, where F is in this polynomial ring of degree homogeneous of degree E, and G is in the same ring homogeneous of degree E plus D. And then this should hold for some E for some integer. And then this symbol here lives in the fraction field because, well, you just have a quotient of two elements in this ring. And we want to satisfy, so until then, it didn't depend on this U. And so the condition that depends on U is that you require that F does not vanish at any point of U. So the denominator doesn't vanish at any point on this open subset, which you consider. And that is the full definition. So these things, as a subset of this fraction field, are just these kind of quotients. And you manually set the OX on the empty set to be 0, because in fact, any sheaf must have 0 or 1 point set on the empty set. Okay, and then the first thing we check is that this is indeed a sheaf of sets. And well, all of these things, so for this we need to first specify what are the restriction maps. And all of these are subset of this fraction field, and we just take the restriction to be the identity. So from here to there, just take the symbol, take it again, send it to itself. And this is well defined because if F does not vanish at any point of the bigger open set, then it also doesn't vanish on any point of the smaller open set. And so the second part, the second condition is still satisfied. So this works out. This restriction is also compatible with composition. If you restrict 2 times, you can also restrict directly. And this then already shows that this is a pre-sheaf. And for checking that it's a sheaf, they'll assume you have some open cover of some open set inside Pn. And so on each element of this cover, you then have these symbols Gi over Fi. And they should be compatible on overlaps. But the good thing is, well, if these two sets are non-empty, then you have open non-empty subsets of Pn, and Pn is irreducible, and we already saw that then they must intersect in some non-empty open subset here. And so then the restriction given by the identity just says then that these two symbols here should be identical in this fraction field. And that meant that, well, on each element of the open cover, you actually had just the same element of the fraction field. And yeah, and obviously in these things, so somehow the denominator didn't vanish at any point of any of the UI, so it also doesn't vanish at any point of the U. And so we find this unique section, which restricts to all of these things on the open cover. And so this then shows the sheaf property. So we have seen it's a sheaf, at least a sheaf of set. But now we put more structure on it. We were interested in these sheaves of modules. And so we're going to slowly work our way. So the first thing that you should be able to do in a module is you should be able to add all of the 2 different sections on the same open set. And so for this, let's say you have 2 of these sections of O of D. And then we have to check, of course, then you can add them just as you would add a formal fraction like this. And we just need to make sure that this thing with the degrees works out, right? Because here in the definition, we want that the numerator always has D more degree than the denominator. And so applying this here, if I just write the degrees here in red, then we can say, well, if this has degree E1, this has degree E2, the denominators, then the numerator must have D more. So we have E1 plus D and E2 plus D. And then if we look at this, well, the numerator now, this is a product, so this has degree E1 plus E2. And here you see we multiply something of degree E1 plus D with something of degree E2. And similarly here, we multiply this with this. And we see in all of these cases, we have E1 plus E2 plus D. So this works out. It's still the case that this has D more degree than the denominator. So plus works, but times doesn't really work. Because if we try to multiply here, then we get this E1 plus E2 downstairs. But we get this degree here is E1 plus D plus E2 plus D. So if we add this all up, we get E1 plus E2 plus 2D. So we see here the addition. This gives us a section of O, P, and D. This is fine, we can add them. But this here, this would give us a section of OPN of 2D, because 2D degrees more upstairs than downstairs. So it's not, in fact, a sheaf of rings in a natural way, except when D is 0, as we're going to see. But we can still add them. So addition works fine. And let's look at this case of degree 0 a bit more. The claim is for D equals 0, we actually have that this sheaf here is isomorphic to OPN, just the structure sheaf. We get back the structure sheaf of PN. And the map looks pretty simple. You just have a section here on U given by G over F. And then by definition, this means that this F and G are of the, this would come plus D, but we are in the case D equals 0. So actually, those two things have the same degree for some E, and the denominator doesn't vanish anywhere. So you're just globally the quotient of two homogeneous polynomials of the same degree. And we have seen this allows us to define a regular function on U. And so we can just send this G over F to the regular function, G over F. This gives a well-defined map. This is because the degrees in this case are exactly the same. It's also injective because somehow if something here maps to 0, then we mean the regular function G over F is 0 everywhere on this open dense subset U. And this forces then G to be actually 0. Because, well, the only polynomial which vanishes on the entire or somehow on U then must also vanish on the closure, and this is dense, so it vanishes on all of Pn. But the ideal of all of Pn, the ideal of functions vanish everywhere, is exactly the 0 ideal by the kind of Nullstellensatz. Okay, so well-defined injective and then surjective, that's something which we haven't seen so much, but it turns out to be true. So let's say we have phi a section here, and then we need to find some G over F mapping to it. Certainly, by definition of a regular function, we find an open cover of this set U such that phi restricted on this open cover is given by some quotient of two homogeneous polynomials of the same degree. That was how we defined the structure sheaf. And well, to avoid any complication, let's say that we exclude all the elements Ui in the cover, which actually have the empty set. And so what we see, so if these are all non-empty, then of course, these two functions agree on this overlap. And the Ui intersected Uj is now still a non-empty open subset. Clearing denominators, we have this equality here. So here, this is now really a polynomial, and it vanishes again on this non-empty open subset. So by density, it actually This polynomial also vanishes everywhere because the vanishing locus of a polynomial is homogeneous polynomial is closed. So we have again something in the ideal of all of Pn, and this is just 0. So in fact, this is not just 0 on this overlap, but it's actually 0 as an element of this polynomial ring. But then we're in good shape because that means that actually this equality here is an equality in the fraction field. And so we are again in a situation, we have this open cover and we have the same element of the fraction field everywhere. And then we can assume, so now we just need to make sure this element of the fraction field doesn't have any zeros, because somehow this denominator shouldn't have any zeros on U. So we need to make sure that we find some representative which has this property. But here we can use that this ring here is a unique factorization domain. And so we can assume by somehow if Fi and Gi at any point have a common factor in their reducible decompositions, we can just kind of clear the denominator and numerator until they are all co-prime. And then once they are co-prime, then this element here of the fraction field is which is the same element of the fraction field everywhere, actually is unique. So you can kind of choose all of them to be the same. And then phi is actually given by this unique fraction on all of ui, and then also on the entire thing u, which they cover. And so we found our element in the sections here, which maps to the given small phi that we wanted. So actually, this proof shows that on any open subset of projective space, actually a regular function always has a global representative as such a quotient. Okay, so what we have learned so far is that we have all these sheaves of abelian groups, and for d equals 0, we get back the structure sheaf. And now we want to what we want to do in order to have a sheaf of modules is we want to have a multiplication map from the structure sheaf and a section of OD to a section of OD. And this is now not so bad. In fact, we can do this much more generally. We can say whenever you have D and E, then you have these two sheaves. And then say you have a common open set U and you have two sections here. Then the claim is you can go to this OD plus E by just taking the two sections and multiplying them in the fraction field. We have actually seen this before. So here, if this is in OD and this is in OD, then after you multiply them, you get a section of OD plus D, namely a section of O2D. And just the same calculation with the degrees here works to prove this statement. Okay. And then if we specialize to E equals 0, then we see we can take any section of OD, multiply by a regular function, because this is now O of 0, so the regular functions, and get a section of OD plus 0, so again in OD. So this gives the desired multiplication map that we want. And then you go through this list of properties that it's compatible with restrictions. All of this works out. And so this indeed becomes a sheaf of modules on Pn. And this is called the twisting sheaf on Pn. Okay. So, I mean, here we just check this list of properties. You can go through it again carefully for yourself. But in principle, describing the sections is not so hard. It's just these kind of fractions of homogeneous elements. So let's do some example computations with these sheaves, and we're going to use many of those later. So first, for such a sheaf, it's always interesting to ask what are the global sections on all of Pn? What can we get? And so assume we had some G divided by F, which is a section on all of Pn. Then if you recall the condition, the denominator is not allowed to vanish anywhere on this open set. So in other words, F is a polynomial in n variables, homogeneous, but its vanishing locus is actually empty. it's not allowed to have any 0, then by the Nullstellensatz, it must lie in the it must be a constant function, and so it lies in k star. But then you're always allowed to divide by something k star. So actually, this g divided by f is an element of this polynomial ring. And since this is somehow the degree 0 elements, the numerator should have degree d more. So this is a polynomial of degree d, homogeneous. Of course, this only works, so this d is allowed to be an integer. This only works when d is at least 0, in which case the global sections are given by these homogeneous polynomials of degree d. If d is less than 0 or less or equal 0, then actually you get just the, sorry, I guess here we want really less than 0, like this. Then you get just 0, because for d equals 0, actually you still get the degree 0 part, which is just k. You get constant functions. Okay. So these are the global sections. But then we can also ask, what are sections on some open subsets? For example, the standard open subset that we like. And there we see that even these sheaves with negative entries can have some sections. So for example, if you take U0 to be these x0, x1, and p1, such that x0 is non-zero, the standard open chart here, then we have an allowed section here. We can take 1 over x0 on this, because now let's go through it. 1 over x0 is an element of the fraction field. The numerator has the degree of the denominator -1. So here we have 1, here we have 0. So this also works out, the homogeneous of correct degrees. And then what we wanted is that the denominator doesn't have any 0 on the set U0, while the zeros of x0 are exactly excluded in this U0. And so this is a well-defined section. Yeah, this works for P1, but also if you just write Pn here, then everything works exactly the same. Okay, and then the other nice thing is then we can get, since we have some global sections here, we also get some actually global morphisms of sheaves here. So for example, if you have a homogeneous polynomial of degree E, this is a section of O Pn of E, then you get a morphism of sheaves from here to there, which sends phi just to phi times this section. So here we use this kind of multiplication map, which goes from D and E and goes to D plus E. So here we just specialize the section to be the sixth thing F, and then we get actually a morphism of sheaves. Everything is compatible with restrictions. So there's some nice maps between these. But in general, so for D not equal to 0, in fact, this sheaf and, for example, the trivial sheaf like this, they're not isomorphic. And to show this, you can just look at the global sections, because if they were isomorphic, then also their global sections would have to be isomorphic as a K-algebra, so as modules over the global sections of OPN on all of Pn. But we have seen somehow we can just distinguish these things. So so here, when D is equal to 0, you get just K. When D is greater than 0, you get a higher dimensional space. And if D is less than 0, then you get a 0-dimensional space. And so both of these are not the same as K. And so the global sections really differ. But so somehow these things are not isomorphic everywhere on all of Pn. But, and importantly, they are isomorphic if you restrict them as sheaves to the standard open cover. So on each of the elements of the standard open cover, you have an isomorphism. And so for this, let's say you take the standard open cover UI when xi is non-zero. then the claim is we have an isomorphism going from here to there, which is again multiplication by a section, namely multiplication by the section xi to the d. So this morphism actually exists. This is part C. This exists globally, but it is not globally an isomorphism. It's only an isomorphism on this ui, if you take here the section xi to the d. And the inverse is here the multiplication with, well, the reciprocal, so with xi to the minus d. So somehow this is just phi divided by xi to the d. And this is allowed here because this xi only has zeros away from the open set that we look at. And so this doesn't add any zeros in the denominator, which are not allowed. And so we get this well-defined inverse. Okay. And so all of this was pretty abstract. We just defined it as symbols, as these elements of the fraction field having certain properties. But in fact, as a kind of small exercise, you can check that some very natural things on projective space are given by these tautological, by these twisting sheaves. And one particular sheaf, which is natural to write down, is the so-called tautological sheaf on Pn. And the tautological sheaf, let's call it F, on any open set U inside Pn, it just gives all the morphisms from this open set U into k to the n plus 1. So here you could also write affine space an plus 1. So it's a morphism of varieties such that you have a kind of set theoretic condition that the image of any point L, remember L in U inside Pn, so Pn is the set of lines through the origin. So we can see this here as a line inside kn plus 1. And we want that phi of this point in Pn, corresponding to this line L, actually lies inside the line L itself. This makes sense because somehow phi goes to this base, which contains all these lines. So you can ask that this vector should be a part of L. And this should happen for all L in this open set. And again, here we mean for all L closed points in this variety U. This gives, first of all, well-defined sets, and then you can check that they have restriction maps because you can just restrict such maps here, and this condition is still satisfied. This makes it pre-sheaf. It's actually sheaf because essentially these are just functions to some target satisfying a condition which you can check pointwise, and so it is a sheaf. And you can both add two such things because lying in this line, having two elements in the line, their sum is again in the line. And you can also multiply these things by functions. Because, I mean, if you lie in a line and you multiply by the value of some function, then you're still in the line. And so this makes this tautological sheaf actually into an OX module. And it's kind of an exercise to prove that this tautological sheaf is actually isomorphic to OPN of -1. If you set d equals to -1, then you get exactly this thing. And in particular, this shows something interesting, which we would have been interested in even if we didn't know anything about sheaves of modules. Namely, it shows that this sheaf here, this tautological sheaf, does not have any global sections. Because if you recall, somehow these OP and D, when D is negative, it doesn't have any non-zero sections. And so somehow it's not possible on all of Pn to choose a vector which varies with the coordinate in the way of such a morphism here, such that you always land in the line, which is parameterized by this. And you could also prove this directly using the things that we have seen, but now we have kind of, with this exercise, we have a second way of showing this. Okay, so these were the twisting sheaves on Pn, the first very important example of these sheaves of OX modules. And this will be our go-to example for various of the constructions we do later, because here at least we have some non-trivial structure and some non-trivial examples.